Try and bring in that money, all right?
I said if I'm gonna go up to Shane and I'm like, hey Shane, he's gonna be like, it's Mr. McCoy.
That's fine. Electron movement. Electron movement, what does that mean? Well, every atom and every molecule in this room in the world has electrons. Hydrogen only has one, but it has one, right? So they all the elements have electrons, and when you make molecules, that's more than one element, more than one atom. So the electron's moving around. So inside these things here, like even simple hydrogen gas, there's electron movement. That creates this dispersion force. More electrons, stronger force. I'd like to add to that here before we get to the video. So what does that mean? Well, take your reference tables out. I'm going to give you 3 examples. See if you can make sense of it. All right, so we got helium, we got xenon, and we got radon. Actually, let's do krypton. Helium, krypton, and radon. I want you to go to table S and look up the density of all 3. Go to table S, look up the density of all 3 elements, helium, krypton, and radon. Now one thing he's going to, the professor, I think he's a professor, could maybe teacher, whatever. Teacher, professor in the video, one thing he's going to say is larger molecules have stronger dispersion forces. I'm not really going to write that down because, so I know I asked you to look something up, look up here. Does it make sense to you that this, look up here, is a larger molecule than this? Yeah, this is CH4 and this is H2. The reason I'm not going to write it in our notes or even stress it too much with you guys is because this more electrons covers that concept. How many electrons does this have? This is CH4. There's 4, but there's more. 8. 10. How do you know? C has 6, H has 1, because it's number 6 and number 1. So this has 10 electrons. CH4 has 10 electrons. This is H2. How many electrons? 2. So again, eyes up here. So this is larger, which means more electrons, which means more electron movement, which means more forces, more dispersion forces. So I just wanted to explain that here. Now, helium, krypton, and radon, they're all just individual atoms. They have different sizes to them. Who would you expect to be the largest? Radon, why? Biggest number, okay.
But easy.
Yeah, it is. Radon's way bigger than helium. It's not even close, but why?
It has more electron levels.
More shells, yes. Focus. Look over there, radon. Period 6. It has 6 shells. Helium only has 1. Krypton has what, 4? 4. So it makes sense that radon gets bigger because it has more shells. All right, let's look up the density now. Anybody want to tell me helium?
0.000164.
Okay.
What?
Krypton?
Shane, density of krypton.
At the bottom.
Number 36. He's got it.
0.003425.
Okay. And Silas radon. Number 86. Tyler, pay attention. Write these down.
0.009074.
Okay. So get those down. All right.
Do their like smaller densities have to do with the fact that they're noble gases, or
1, they're monatomic gases. 2, they're noble gases. Yeah.
okay?
And it has to do with exactly what we're learning, and I'm hoping you realize that. Why did I just write those 3 down, Jake? why did I put that underneath the notes that say more electrons equals stronger force? What do these have to do with that statement?
So which one has the strongest force?
Very good. Okay, which one has the strongest force? Radon. How do you know that?
It's more dense and it has more electrons.
Very good. Good job, Jake. So more dense means the particles are getting sucked in, right? So radon, even though all three of these are really, 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 really small numbers, right? I mean, these are very small numbers. Okay, what's the density of water? Anybody know? One. It's one.
Oh,
One
yeah.
very
To
familiar.
see that.
Yeah. So water is significantly more dense than these gases, which makes sense, right? Because think of the air. If I have water in this room, the water doesn't float on top of the air. It's the other way around,
That'd be
right?
cool.
So the air is less dense. So gases are less dense than solids and liquids. Why is that? Focus. Eyes up here. Why are solids and liquids more dense than gases? They're closer together because they have stronger forces. Right, you learned that way back in the fall when we did physical chemical changes. I started with the concept of forces of attraction. Why? So that all year we kind of talk about it. When you get to this, it makes hopefully complete sense. That radon's going to have a larger density than these two because of what we're learning here. It has stronger dispersion forces. Why? More electrons. What does that cause? You're going to see that in the video. But it causes these forces to be stronger. Radon's a low-lying gas. You find it in basements of houses. You buy a new house, you have to get radon levels tested. It's like a New York state law. You can't buy the house unless that radon test comes back acceptable. You don't want too much radon. It's not good to breathe in. But they put the sensors in the basement, not in the attic, because that doesn't make sense. It's very dense. I know that's a small number, but in relation to other gases, that's pretty dense. All right. Helium is one of the least dense gases there are. Which gas do you think is less dense?
Helium.
Hydrogen, it should say.
It's helium.
What's hydrogen? What?
0.00002.
4 zeros, right? Yeah. So I'm just trying to help you understand. If you look over here, group 18, as you move down that group, you see the numbers get bigger, more electrons. The atoms get bigger, more electrons. What does that mean? More forces. What does that mean? A greater density. It also will affect boiling points and melting points. Okay. All right, what else did I want to write before I show you the video? Oh, one more thing underneath that. Put a star, this is important. So you try and, I guess I'll just say memorize. It would help if you can memorize this, just remember it. Non-polar substances have only, capitalize only and underline it, dispersion forces. There's no other force non-polar molecules have. So the ones I've been talking about, CH4, CO2, the Honkobriffs. And again, you're supposed to learn that already before break and with that molecule lab. So that term, non-polar, should make some sense to you. It's symmetrical, equal sharing, equal distribution. The forces are really weak. Remember the lab with the aluminum foil or the tin can lid? You put it over the candle. 3 melted, 3 did not.
No.
Okay. What was the point of that?
Melting
Forces.
points.
The ones that didn't melt are stronger, and those were ionic.
Yeah.
The ones that did melt are weaker. They are
Covalent.
covalent. Specifically, non-polar covalent. That means they have the weakest force. Dispersion are the weakest by far, and that's because they're temporary. They form, they break, they form, they break. What's the? What am I doing here to show you a force? Handshake, right? I can shake Tyler's hand, Renee's hand, I can shake everyone's hand, but I have to let go. Can't shake her hand the rest of the day, the rest of my life. That's weird,
Yeah.
right? So, no, I'll lose that bet. I can't, you don't shake hands with somebody for the rest of your life. It's a temporary action, just to say, hey, how you doing? And then you let go. That's kind of what these forces are. They form, they say, oh, how you doing? And they let go. All right, so they're very weak, but some molecules and particles have more dispersion forces or less. They're still really weak, but this one's stronger than this one. It's relative. Yeah.
Now you say only.
Yeah.
Is this true?
It is true.
There's
So
no-
out of
Then
those
there's solids.
four options. You have dispersion, you have dipole, you have hydrogen bonding, and you have ion molecule or ion dipole. Pure. So this right here, hydrogen gas, nonpolar substance, only uses dispersion. There's no other force it could possibly use. That is not. I'm not withholding further truth there.
He's keeping
I
secrets.
thought network solids didn't have any forces.
They don't. They're not nonpolar.
Oh, okay. I thought you said all atoms and molecules had them.
Oh, I see what you're saying. Those are kind of different. It's not. Those aren't really molecules or atoms. They are molecules. I don't want to confuse you, but they're like mega molecules because they're all bonded to each other.
Okay.
So we're using that term all loosely.
Okay.
Good question. All right. What else did I want to tell you before I get to the video? I think that was it. All right. Here's the video. I'll tell you what else you need to write down as soon as I put it up here. Oh,
That's right.
Can you guys get the first 3 blinds, please? Can you not? Or shades, whatever.
Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 16. It's on London dispersion forces,
Teacher, not
which were
professor.
first identified by Fritz London. That's where they get their name, after this whole idea of quantum mechanics had been developed. Can you find him in this picture? He is right here. But before...
What's wrong with him?
He's looking at what?
Yeah,
Yeah, he's the only one not looking forward. I thought that was bizarre. That doesn't mean anything's wrong with him, but.
we move on and talk about it, think about the forces in this molecular forces. Those are going to be the forces between the molecules, between this molecule and this molecule, between this molecule and that molecule. And these are generally going to be really, really low compared to the intramolecular within the molecule itself. And we'll talk more about those in later videos. But London dispersion forces are going to be attractive.
So just to be clear, intra, that's the bonds. Inter would be if these two were attracted, that's the inter. It's the dotted line, the handshake. That's inter. Intra is the bonds. So intra are way stronger.
Forces. These are intermolecular, between molecules, and they're going to be found in all atoms and molecules. So everything is attracted through London dispersion forces. Really important. What really develops them are uneven electrons. As the electrons are distributed unevenly, they create what are called a temporary dipole. Those are going to be a molecule that has a charge. It has a positive and a negative charge. These are going to increase as we increase the contact area between the molecules. Also, as we increase their polarizability, which is going to be the squashiness of a molecule. Generally, the more electrons you have, the higher this is going to be. And so as we increase molecular size, we're going to increase these dispersion forces. And finally, pi bonding, which is going to be where orbitals overlap. If we have more pi bonding, we're going to increase.
All right. So you don't need to know about polarizability, pi bonding, or contact area, surface area, but I'm going to try and help you understand that. Okay? Take your 2 hands. Let's go, Renee. Get involved. All right? Point. Okay, now put the 2 tips of your fingers together. Okay, now, is there a lot of contact area between your fingers? No. Can you create more contact area?
Yes.
How?
Like that.
Okay, turn them this way, right? Okay, now, make 2 fists like you're going to punch somebody. Don't punch that. Now, if you put your fists together, okay, there's a certain amount of contact. Can you increase your contact area of your hands?
Yes. Yeah.
Yes.
Oh wow.
There's more contact there.
Easy.
Right? Would we agree?
Yeah.
So, dispersion forces in molecules, some molecules look like a sphere, kind of like your fist. Some molecules, this is harder to explain, are more like a flat hand or flat palm. And the way it actually works is the smaller number of carbons, the more spherical it looks. So if we were to kind of connect all of these angles here, you could almost see it kind of looks like a ball, sort of. And you have to use your imagination. Kind of like, constellations, they come up with crazy shapes, like where they get that from. But anyways, 1 carbon is more spherical. That's like your fist. If I was to connect like 30 of these carbons, and it would kind of look like this. I didn't get anything put together, sorry. But if I was to connect 30 carbons, it would be a long chain. And that long chain kind of looks like this. Or like imagine two pieces of rope or something, strings, and you hold them right next to each other. There's a lot of surface area. So what he's talking about with surface area is that. So some molecules look like this. Big long carbon chain. And if you take another carbon chain and bring it alongside of it, they form dispersion forces in between them. Whereas if you have one carbon and another carbon, there's only one little area, it's kind of like your fingers, only one little area that they can connect or attract versus when your palms are touching. So the bigger, longer molecules have stronger dispersion forces. I took some time to explain it because I think it's good for you to hear that, but it's not on the readings. All right, that's actually a really important concept moving forward in upper level chemistry and really why certain things are attracted and certain things aren't, not in regions. So let me spell it out. What do you need to know? Well, you need to know how to draw dispersion, and I'm going to show you that with this. He's going to show you. You need to know what we talked about with moving down group 18 there, so helium, krypton, radon. As they get bigger, more electrons, more forces. So you need to know how to draw it, how to explain maybe group 18, right? As you move down, it gets stronger. And all nonpolar have dispersion. So those are the things that the regents will focus on. All right, so you're going to copy this in your notes in a minute. I'll stop it and tell you what to draw.
Increase these. And so let's look at it. Why are London dispersion forces important? Well, they're in everything. And if it weren't for them, we'd never have noble gases in a liquid phase. And we know we can do that if we can cool it down. And so what holds helium together when it gets into this liquid phase is going to be these London dispersion forces. So right here I have two helium atoms, and so they're going to have two protons on the inside, two electrons on the outside. And so as we move them close together, watch what happens to the...
Okay, he moved them closer together. What happened to the electrons? They moved to what side? Right, so left, right? So this circle and this circle represent the red and the red, right? So inside would be the protons, that's +2. The electrons are outside the nucleus. So when they get close together, the electrons line up on the left side. So if I was to split these atoms in half, we have the left side, the right side, the left side, the right side. Raise your hand. Don't shout it out. Raise your hand. Which side would be partially negative? Which side would be partially positive?
The left side negative, the right side.
Yeah, so this side is partially negative, and this side is partially positive. This one looks exactly the same, so that's partially negative and partially positive. Those are called temporary dipole.
They're electrons. Let's watch that again. As they move close together, the electrons are going to migrate. What's doing that? Well, the electrons on the outside of one helium are going to be attracted, just Coulomb's law, to the protons on the inside of that other helium. There's also going to be repulsion between those electrons on the outside. And so what this really is creating are two what are called temporary dipoles. They have positive and negative ends. And so a London dispersion force is simply going to be the connection between...
Okay, you're going to draw that. I prefer you draw it the way I have it here. There's your dotted line. There's your dispersion force. And that's it. That's all that we're going to basically end with that as far as dispersion forces. Then we got to, we only have maybe like 7 minutes, but that's all I need. The next three forces go very quickly. Everything we just learned about dispersion, you apply to the other forces, it's just a little bit different. So that's what causes dipole, dispersion. It's when those electrons kind of move and migrate to one side. And if they're on one side, that's partially negative. Well, the other side's going to be absent of electrons, so it's partially positive. The opposite charges will attract, and that's called dispersion. Why is it so weak? It's temporary, like a handshake. Okay, your arms attached to your body, that's permanent. I hope so. That should be, unless something very wrong happens. All right, so that's the analogy there, right? The bonds holding your arms on, that's permanent. But this force, the handshake, is temporary, and you can shake whoever's hand you want, and then let go and shake someone else's hand. That's exactly what gases do. They shake hands, they break free. They shake hands, they break free. That's why gases are always moving. So, really weak force, but that's how it's formed with temporary dipoles. So on your homework, all the non-polar molecules, you need to draw this. All right, this is why I'm having you do it. Good. Next, dipole interaction, dipole, and that would be, nope, there it is. Okay, so dipole interactions, write this in your notes, please. These are stronger than dispersion because these dipoles are more permanent. So the example here, well, I'm going to write this in your notes first. Polar molecules have dipole interaction. And again, we've already learned that, so I don't really need to reteach it. I don't have time to. So you should understand when I say polar because they have dipoles. So HCl is a great example. HCl bonded to, H bonded to a Cl, H bonded to a Cl. Because that Cl has such a high electronegativity, it pulls all the electrons, creating that dipole moment. Cl is partial negative, H is partial positive. That negative positive, the dotted line here, that is your dipole force. It's not the same as the dipole in the molecule, not the arrow. That's the bond. The force between two molecules is what I'm talking about. That's your dipole interaction. But these are stronger because the dipoles within the molecule are permanent. So that HCl always has those partial charges. Back to dispersion, they're not always like that because electrons can move however they want. So again, this is more permanent. That's why these are stronger. Okay, so you got your dispersion forces, you got your dipole interactions. There's no other notes really to give you on this. You just need to understand anything with a dipole, polar, has this force. So it's more kind of like on you guys to remember, not a whole lot to figure out. You just need to figure out, okay, which molecule is polar? Well, polar is held together with dipole. Just kind of, you got to put those together in your mind. I don't have any tricks for you there. Sorry. Okay, but similar, right? They're using those partial charges. It's just this one is stronger. Okay. So that's dipole. Next, hydrogen bonding. And this is the strongest of the three. Hydrogen bonding. This is any molecule that has H with, so any molecule that has hydrogen with nitrogen, oxygen, or fluorine. So any molecule that has an N with an H, an O with an H, an F with an H, or you can say it the other way around, H with an N, H with an O, H with an F. Any molecule with those elements have hydrogen bonding, or has hydrogen bonding. Water has hydrogen bonding. We drew it today as the warm-up. Okay? We'll do another one here. HF. HF is attracted to HF. It looks literally the same as HCl, except it's special because it's an F, not a CF. I'm going to explain why in a second. H is partially positive, F is partially negative. So again, nothing new here. Those partial charges. This dotted line between F of one and H of another, that's called your hydrogen bond. There's your H bond, that dotted line. So what makes hydrogen bonding special? It's basically the exact same thing as a dipole, but it's stronger, and the reason for that, I guess I'll write it right here. This is strong due to high electronegativity of the N, O, and F. Because nitrogen, oxygen, and fluorine have really high electronegativities, it makes these dipoles way stronger. Because they're way stronger, the attraction is stronger, which is why water, for example, has a much higher boiling point than HCl, way higher. HCl is actually exists as a gas. Water is a liquid, so. The last force, I know I'm going quick here at the end, is this one. You've already learned this. This is ion dipole or molecule ion. This is like salt water. So when you put salt in water, the salt is attacked by the water and the water rips it apart. The oxygen faces the Na+, whereas the Cl-, it would be the hydrogens that are attracted to the Cl. Again, I know I'm going fast, try and get this down. You've already seen this. This should not be anything new to you guys. You've already seen this. I'm just giving it a name. This is called molecule ion attraction. The ion is Na+, Cl-. The molecule is the water. So what is molecule ion attraction? It's when something ionic is dissolved in water, so like salt water, for example. So that's molecule ion. Pretty strong force, but not that strong. How do you separate it? How do you get the water and the salt back?
Filtration.
Boil it.
Heat.
You just boil it, right? And then the water reforms, and then the salt reforms, right? But it is a strong enough force, stay with me, right to the bell, stay with me. It is a strong enough force, hold on, give me 10 more seconds, finish my thought. It's strong enough to allow the salt to dissolve. If it wasn't attracted, it wouldn't dissolve. Like dissolves like. All right, that's it. So, do that worksheet for homework. We'll talk about it tomorrow.
I don't know why I keep doing that. Post it on your YouTube channel.